This is day 21 of Advent of Cyber, and today's challenge is called Have Yourself a Merry Little Webcam. After investigating the webcam implant through hardware and firmware reverse engineering, you're tasked with identifying and exploiting any known vulnerabilities in the webcam. Elf McSkitty is confident you won't be able to compromise the webcam as it seems to be up to date, but we will investigate if off-the-shelf exploits are even needed to take control of the workshop. The learning objectives are explain the Internet of Things, why it is important and if we should be concerned about the danger, understand the difference between an IoT-specific protocol and other network service protocols, understanding what a publish-subscribe model is and how it interacts with IoT devices, analyze and exploit the behavior of vulnerable IoT devices. The Internet of Things defines a categorization of just that, things. Devices are interconnected and rely heavily on communication to achieve a device's objectives. Examples of IoT include thermostats, web cameras, smart fridges, to name a few. While the formal definition of IoT may change depending on who is setting it, the term can be used as a broad categorization of a device that sends and receives data to communicate with other devices and systems. If IoT defines such an extensive categorization of devices with varying capabilities and objectives, what makes them important or warrants that we study them? While several justifiable reasons exist to study IoT, we will address the three possible answers. First, IoT categorizes unique devices, e.g. smart fridges, that don't match other categories, such as mobile devices. IoT devices tend to be lightweight, which means that the device's functionality and features are limited to only essentials. Because of their lightweight nature, modern features may be left out or overlooked, one of the most concerning being security. While we live in a modern era of security, it may still be considered secondary, which is why it is not included in core functionality. Second, devices are interconnected and often involve no human interaction. Think of authentication in which a human uses the password for security. These devices must only be designed to communicate data effectively, but also negotiate a secure means of communication, such that human interaction is not required, e.g. using a password. Third, devices are designed to all be interconnected, so if device A is using X protocol and device B is using Y protocol, it presents a significant problem in compatibility. The same concept can be applied to security where devices are incompatible, but could fall back to insecure communication. Security is often thought of as a secondary, so not ensuring a device can securely communicate with other devices may be a fatal weakness that's overlooked or deemed less important. An IoT protocol categorizes any protocol used by an IoT device for machine-to-machine, machine-to-gateway, or machine-to-cloud communication. As previously defined, an IoT device sends and receives data to communicate with other devices and systems. With this in mind, an IoT protocol's objective should be efficient, reliable, and secure data communication. We can break up IoT protocols into one of two types, an IoT data protocol or an IoT network protocol. These types may be deceiving in the name, as both are used to communicate data. How they differentiate is how and where the communication occurs. At a glance, an IoT data protocol commonly relies on TCP/IP model, and an IoT network protocol relies on wireless technology for communication. We'll continue expanding the purpose of these protocols in below. An IoT data protocol is akin to common network services you may use or interact with daily, such as HTTP, SMB, FTP, and others. In fact, HTTP can be used as the backbone for other IoT protocols or as an IoT data protocol itself. An IoT network or wireless protocol still maintains the same goals as data protocols, that is, data communication, but achieves it differently. Rather than relying on traditional TCP protocols, these protocols use wireless technologies such as Wi-Fi, Bluetooth, Zigbee, and Z-Wave to transfer data and communicate between entities. Because data communication is a primary objective of IoT data protocols, they commonly take the form of a messaging protocol. That is, the protocol facilitates the sending and receiving of a message or payload between two parties. Messaging protocols communicate between two devices through an independent server, middleware, or by negotiating a communication method amongst themselves. Devices commonly use middleware because they must be lightweight and efficient. For example, an IoT device may not support a more robust protocol such as HTTP. A server is placed in the middle of two clients who want to communicate to translate the communication method to a means both devices can understand, given their technology. The compatibility of device protocols could be a problem. Middleware fixes some of the associated issues, but may still be unable to translate all communications. Popular messaging protocols used by IoT devices are message queuing telemetry transport, which is a lightweight protocol that relies on publish-subscribe model to send or receive messages. Constrained Application Protocol translates HTTP communication to a usable communication medium for lightweight devices. Advanced Message Queuing Protocol acts as a transactional protocol to receive, queue, and store messages or payloads between devices. Data Distribution Service, a scalable protocol that relies on publish-subscribe model to send and receive messages. HTTP, used as a communication method from traditional devices to lightweight devices or for large data communication. And WebSocket relies on client-server model to send data over TCP connection. Messaging protocols commonly use a publish-subscribe model, notably the MQTT protocol. The model relies on a broker to negotiate published messages and subscription queues. Let's first look at the diagram to see how it works. So first, you have the publisher that sends a message to the broker. The broker continues relaying the message until a new message is received. The subscriber is asking, are there new messages? And if there are, then the broker will send the new message. The protocol should work fantastically if a single broker is needed for one device's objectives. But what if several types of data need to be sent from one device or several publishers, and subscribers need to connect to one broker? Using more than one broker can be feasible, but increases unnecessary overhead and server usage. A secure communication method should also ensure the integrity of messages, meaning that one publisher should not overwrite the other. To address these issues, a broker can store multiple messages from different publishers by using topics. A topic is a semi-arbitrary value, pre-negotiated by the publisher and subscriber and sent along with the message. The format of a topic commonly takes the form of name, ID, function. When a new message is sent with a given topic, the broker will store or override it under the topic and relay it to the subscribers who have subscribed to it. Below is a diagram showing two publishers sending different messages associated with topics. Below is a diagram of several subscribers receiving messages from separate topics of a broker. Note the asynchronous nature of this communication. The publisher can publish at any time, and the subscriber can subscribe to a topic to see if the broker relayed messages. Typically, subscribers and publishers will continue attempting to connect to the broker for a specific duration. A publish-subscribe model is helpful for any data maintained asynchronously or received by several different devices from one publisher. A common example of a publish-subscribe model could be a thermostat publishing its current temperature. Several thermostats can publish to one broker, and several devices can subscribe to the thermostat they want data from. As a protocol specifically, MQTT is also lightweight, with a small footprint and minimal bandwidth. Are IoT protocols inherently vulnerable? We've identified the relation between IoT protocols and network services and how message protocols function. It still leaves the question of how secure IoT protocols are. Let's apply this to something we are more familiar with, HTTP. HTTP vulnerability is often referred to a vulnerability in the software or application built off the protocol. This doesn't mean the protocols are absent of vulnerabilities, but they generally possess strict requirements and require revisions before release or public adoption. Similarly, IoT protocols are not inherently vulnerable, so what makes an IoT device insecure? Before giving a more formal explanation, let's just consider the default settings of MQTT. When it is first deployed, an MQTT broker assigns all devices connected to read-write access to all topics. That is, any device can publish and subscribe to a topic. We may be okay with this at first, in the thermostat example, if we are only communicating temperatures, so the integrity of the data should not be an issue. But let's dive into this issue more. Our data should follow CIA, confidentiality, integrity and availability best practices, as closely as possible. That is, data should not be read or manipulated by unauthorized sources and should be accessible to authorized users. Following best practices, authentication and authorization should be implemented to prevent potentially bad actors from compromising any principle of the CIA triad. What is the risk to IoT devices if best practices are not considered? Risk is almost solely dependent on the behavior of a device. Let's say a device trusts an MQTT publisher and passes data or commands to perform actions affecting the device's settings. An attacker could send a malicious message to perform unintended actions. For example, a thermostat sends a message with a specific format to a broker, and a subscriber passes the message and changes the temperature. An attacker could send their message outside of the intended application, a mobile app, to modify the device's temperature. Although this example may seem modest, imagine the impact this could have on the other devices with consequences or critical devices, which are essential to the function of a society and or economy. To recap, an MQTT instance may be insecure due to improper data regulation best practices. An instance may be vulnerable if the device's behavior allows an attacker to perform malicious actions from expected interaction. Note the differentiation between insecure and vulnerable. An insecure implementation may allow an attacker to exploit a vulnerability, but this does not mean the implementation is inherently vulnerable. Before moving on to the hands-on section, let's address how we can identify information about device behavior. We've defined that IoT devices are vulnerable because of their application's behavior. Now let's briefly look at how we can analyze a device's behavior for vulnerable entry points and how they can be abused. An attacker can discover device behavior from communication sniffing, source code analysis, or documentation. Communication sniffing can determine the protocol used, the middleware or broker address, and the communication behavior. For example, unencrypted HTTP requests are sent to a central server, which are then translated to COAP packets. We can observe the HTTP packets and look for topics or message formats that vendors should have, e.g. settings, commands, etc. to interact with the device. Source code analysis can give you direct insight into how a device passes sent data and how it is being used. Analysis can identify similar information to communication sniffing, but may act as a more reliable and definite source of information. Documentation provides you with a clear understanding of the standard functionality of a device or endpoint. A disadvantage of only using documentation as a means of identification is that it may leave out sensitive payloads, topics, or other information that's not ordinarily relevant to an end user that we, as attackers, want. Once a behavior is identified, we can use clients to interact with devices and send malicious message or payloads. Most IoT devices have a device ID that they use to identify themselves to other devices, and the other devices can use to identify the target device. Devices must exchange this device ID before any other communication can occur. In the case of MQTT, a device ID is commonly exchanged by publishing a message containing the device ID to a pre-known topic that anyone can subscribe to. Once an attacker knows the device ID and behavior of the target device, they can attempt to target specific topics or message formats. These topics may trust the message source and perform some action blindly, e.g. change a temperature, change a publishing destination, etc. In our scenario, preliminary information has been identified by Recon-McRed through hardware analysis and firmware reverse engineering. The web camera device is known to use the MQTT protocol, and we have a list of potential topics we can target. Before analyzing these potentially vulnerable topics, let's look at how we may interact with the MQTT endpoint normally. Different protocols will have different libraries or other means of interacting with them. For MQTT, there are two commonly used libraries that we'll discuss. That's Payho and Mosquito. Payho is a Python library that offers support for all features of MQTT. Mosquito is a suite of MQTT utilities that include a broker and publish-subscribe clients that we can use from the command line. In this task, we will introduce the Mosquito clients and their functionality. In the next task, we will leverage the clients against a vulnerable device to get hands-on. By default, the subscription utility will connect a local host broker and only require a topic to be defined using the -t or --topic flag. Below is an example. So mosquito sub -t device /ping. You can also specify a remote broker using that -h flag. Below is an example of connecting to example.thm and subscribing to the topic device /thm. Mosquito sub -h example.thm -t device thm. We can use the mosquito pub client to publish to an MQTT broker. So to do that, we can do mosquito pub -h example.thm -t device -info and then -m for message. This is an example. We've covered all the information needed to successfully approach exploiting an insecure data communication implementation of an IoT device. Let's try to take what we have learned and apply it to unknown web camera identified in Santa's workshop. So we now need to start the challenge machine and attack box, so I'll do that and be right back. Okay, so let's continue. As briefly covered previously, we know the following. The device interacts with an MQTT broker to publish and subscribe to predefined topics. The device is at the machine's IP address. From firmware reverse engineering, we know that the devices use these topics, device/init, publish the device ID of the current device with device/id/cmd, subscribes to the device ID specific topic to receive commands and settings. If a device is known to use RTSP, the device is known to use RTSP, real-time streaming protocol, for input streaming. If an attacker can control where and how the RTSP stream is forwarded, they can redirect it to an RTSP server they control. The device ID command topic can specify behavior through a numeric CMD parameter and the ability to pass a key value pair to be used to interact with the device. We do not yet possess how the command topic behaves or the format it is expecting the message. It is up to you to craft a malicious message to target the command topic. If you are looking for a challenge, we have provided you with a small source code snippet extracted from the device firmware that you can use to gather communication behavior. Otherwise, we have collected the information you need with the expected format and behavior of the device. So let's take a look at this. Okay, so it receives the payload, decodes it, it gets rid of the curly braces because it's key value pairs, it splits it by a comma. Okay, so then the payload, so there's a command, the payload has a command and a URL, so grabbing the payload, the command which comes first and the URL payload that comes second, and then you're splitting by the colon because it's key value pair, so split by that. Command, payload name, oh yeah, so index 0 is the key, then 1's the value, key value. So if it is a command, then if command value equals target CMD, so target CMD equals 10, so command value match. So then if, okay, the URL is URL, then URL payload value. Okay, then it's writing to a file the URL, and when it's done that, it will run a sub process. Okay, so that's the function. And you can do client.subscribe topic, then client.onMessage equals message. Okay. So expected device behavior. Okay, yep, key value pair of CMD value, URL value. Note, the format for quotes must match exactly and double quotes must wrap the entire message. The CMD value to overwrite redirect the RTSP URL is 10. Yep. The URL value should be ETH0 or ENS0 interface of the attacking machine hosting the RTSP server and an RTSP path of your choice. Okay, so to get started, we have provided steps for exploitation. So verify that this is an MQTT endpoint and users that expect to port them up. So let's do that. Okay, so what we're doing is nmap 10.10.169.163. So we can see that SSH and HTTP is up. So use Mosquito sub to subscribe to the device init topic to enumerate. So if we go back up and find the command, it will be this. So mosquito underscore sub dash h 10.10.169.163 dash t device slash init. Okay, so we've received a value there. So just subscribe topic to enumerate the device and obtain the device ID. So start an RTSP server using this. So let's grab this docker command, open up a new terminal, and we'll put that docker command into the clipboard first, and then we'll paste it in and run. Okay, so that seems to be running now. Then use Mosquito pub to publish your payload to device ID CMD topic. Recall that your URL must use the attack box IP address or respective interface address you're using for VPN. Okay, so it'll be like that. Open up a new terminal, and in here it will be, say, mosquito pub dash h 10.10.169.163 dash t device slash init, and for payload it's dash m, and this is inside of curly braces. Actually, that's not the topic. The topic is our ID, so that is this value here. So we'll type that in, then slash cmd, and the message is cmd colon 10, and then URL colon RTSP colon / this device's IP address, which is 10.10.159.1214, and its port, I think 855, yep, 855.8554 / path. But also must put quotes around this. So let's quickly do that, and let's submit and see if that works. Okay, I think the message needs to be wrapped in single quotes, so let's do that. Now let's submit. Okay, let's carry on with here. So publish a payload to device / ID / command device / our ID. It's possible that I wrote the ID wrong, so I'm just going to double check. That seems to have been correct. So RDSP colon / 10.10.159.214 port 8554. Okay. If the message was correctly interpreted and the RTSP stream was redirected, the server should show a successful connection and may output warnings from drop packets. You can view what is being sent to the server by running VLC and opening the server path of the locally hosted RTSP server. Okay, so let's copy this. Need to put into the attack box clipboard first, and then do that. Okay, well that hasn't worked. Maybe it was meant to be lowercase. Let's see if that's worked. And let's see if this, going back to VLC, works. Something that we could try, looking at this command, we could put the 10 in quotes, like so. Let's see if that does anything. Okay, that seems to have not worked. What we can also try is maybe doing triple quotes around these instead of a single quote. Okay, that seems to have worked, as we're now getting connection here. So now let's rerun the VLC. Oh, and there we go. We've now got the feed. Okay, cool. Okay, so let's answer the questions now. What port is Mosquito running on? That was 8554. Or not. Port 8000. Okay, I guess we can use this nmap command, because we didn't get any port numbers before when we ran it. Anyway, while this is running, let's go to the other questions. Is the device /init enumerated by mmap during a script scan of all ports? No. Okay, I guess we also got another mmap command to do. Okay, well that's running, we'll go... Okay, so this has found port 1883. So we can put that in for the first question, 1813. Okay, that's that. What mosquito version is the device using? Okay, so we can run this topic. We'll go here, mosquito sub, and we will put that topic here and paste that. While that's running, let's continue. Okay, the flag from the video stream is in the video, so THM, your camera is mine. Your camera is mine. Okay, so I'm going to be waiting for this to finish, so once that's done I'll be right back. Okay, so this mmap command has finished running, and as we can see it's going through all the different topics on the mosquito publisher. So we can see here, device init, so we can do yes here. And for the mosquito version, well, running it in here didn't work, but it was able to retrieve it here, right here. So mosquito version is 1.6.9. 1.6.9, and that is day 21 of Advent of Cyber completed. If you like this video, make sure to like and subscribe.